All right, so let's recap here just a little bit what we were talking about last time. I know as we kind of transition here into this uh, online format, um, especially with a course like this Bioinorganic, where I'm kind of basing what I teach you guys off of what you guys respond. Then I just want to take a quick moment and say that if I'm going to be moving all to online here, right, then there's got to be a match from you guys in the sense of making sure that you guys are giving me the feedback, like, hey, I don't understand this, or could you go over this again, whatever that might be. I'm going to record lectures, or a couple of lectures, and we might transition into a face-to-face. But we'll kind of see what's going on with this here, okay? But I wanted to finish this lecture. This should take us, through Wednesday, and then maybe on Friday we'll go to face-to-face lectures here, right? While we all kind of get settled in with everything. But if you recall, what we're going through is we were talking about molecular orbital diagrams, right? Let me go back up here, right? We're going through molecular orbital diagrams. We talked about the different components of this and how they go together, and what the purpose is. And I really want to emphasize this purpose, right? The purpose of a molecular orbital diagram is to show us a couple of things. The relative energy levels of the molecular orbitals, right? We know that antibonding orbitals always have to be higher in energy than their corresponding bonding orbitals. But that doesn't mean that all antibonding orbitals are above every bonding orbital, okay? So I'll show you guys what we mean here in just a second, right? We also recall that the electrons live in these orbitals, and the electrons are the things that are going to do chemistry for us. We also made the point that when we are going to be dealing with our metal ions in our enzymes and our proteins, the electrons are going to be living on the metals, and so the highest and the lowest occupied orbitals are typically going to be on the metal themselves. That means that the chemistry is going to be happening on those metals. So what we're going to do is we're going to, do a couple examples of molecular orbital diagrams, and then we're going to build this into how do molecular orbital diagrams look on the metals, because that idea and that structure is going to be what we need to kind of explain how the metals behave within these enzymatic systems, okay? So anyway, remember we went over and we looked at the molecular orbital diagrams for hydrogen and helium, and we talked about bond order and what the shapes are and angular overlap and all these ideas that go into this, right? And there is a lot that goes into this. There is a lot. We are flying through this at the moment, right? We're going really, really, really fast, right? Remember, I told you guys that when I was taking this course in graduate school, a more advanced course, a version of this, of course, right? But we spent weeks and weeks on molecular orbital diagrams. There's some other things behind the scenes, which I'll briefly introduce in one of the other classes, but there is stuff going on behind the scenes, and so if you're looking at this and going, well, what in the world, how did we get here, what does that mean, all this kind of stuff, right, there is some other stuff going on, right? Anyway, from there, we went and started to construct a more complex molecular orbital diagram, that is one for O2, and there is a couple of things just to understand about this. We started with the easier stuff. We went there and we overlapped our two s orbitals, right? We brought our spherical orbitals together in their bonding and anti-bonding combinations. The bonding combination, right? One of the homework assignments I guess I gave you guys was to draw what the new orbitals look like, right? In this bonding combination, right? So we have an overlap of those two orbitals, okay? So the two spheres would come together to form some kind of bonding combination in there is what it is, right? And the anti-bonding combination would be, whoops, I put that on the wrong side, would be on the opposite of this, right? So we got red, we got blue, right? So we got one in phase and one out of phase combination. It doesn't matter whichever one you want to pick. That's just fine like that, right? All right. And then we said, okay, that's pretty easy. That looks very similar to the hydrogen example that we had previously. Let's take a look at what's going on with our p orbitals. And so remember, we're going to approach this in a visual manner. I'll talk very briefly about when you have a non-visual system, right? How we do this, let's say mathematically, but we'll one step at a time, right? Anyway, here, so we drew a representation, right, where the red and the green, the red and the blue dots there are our nuclei. And so let's take a look at our px, our py, and our pz orbitals, okay? So our px orbital here, right, if we have basically our lobe, okay? That's how these would look, right? If you imagine if we brought these two together, right, if we brought these two together as these atoms approach each other, would this make a bonding combination? Right? Well, remember we're going to have a head-on, right, head-butting, right, a head-on collision of these two orbitals, so would that make a bonding combination with our px? Well, yes, it would, right? You can see how this, this orbital would overlap with that orbital there to make a bonding combination, okay? So we have that head-on overlap of those two orbitals. So let's go up here, right? We'll bring our px, right? We'll bring our px. Remember, if we are making a head-on collision, right, sigma 2p, that would be a sigma bond that we form, right? And we would form the corresponding anti-bonding combination, right? So sigma star 2p orbital. Cool. So let me pause here for just a second, right? Let me erase this, right? Whoa, no. Not what I wanted to erase. That's okay. So what I want to show you guys real quick is just kind of some of this visualization here, right? So what does and what doesn't make a bond. So let's imagine that we bring in the px orbital there in the red atom, but let's bring in the py orbital over here, okay? What would happen if we mix these two orbitals together? Well, the answer is nothing, right? So let's just bring this, right? Let's just visualize these coming closer together and let's see what happens. So essentially, right, we would see an overlap like this. This phase would overlap, but this phase here would cancel each other out. Do you guys see what I mean with this, right? The other way of thinking about this is right here in the middle, right? Let me get a different color here, green. Okay, so right here in the middle, that's a node, right? That's a node for that py orbital, which means that electron density can't exist along that node, right? So essentially we're saying, hey, can we bring a region of electron density along the node for another orbital? Well, the answer is no, you can't do that, right? Electron density can't exist there, right? That's not the way this thing works, right? But if we imagine visually, right, if we bring these two together, we will have a region of overlap and we'll have a region of canceling out. So this is a non-bonding interaction, right? This is not going to give us any kind of bonding interaction. So our px and our py can't overlap with each other, okay? All right, so let's erase this, and hopefully you guys can start to see where this is going to go, right? We could make the same argument here, right? Just for argument's sake, let's do it. What if we have the pz and the px orbitals coming together? Right, this is a little bit more difficult to draw, at least for me, because I stink at drawing, right? So, think about it. The pz orbital is coming out of the screen towards you, right? So if I try and draw this a little bit down here, right, it'd be the equivalent of, right, there's one lobe coming out towards us, right, and there's another lobe there in the back. Boy, is that terrible, I know. I'm sorry. Hopefully you guys can visualize this, right? We have the same instance that we just had drawn there, right? The py orbital here is coming in on the node of the pz orbital, so electron density can't live there, okay? So again, this would not form a bonding combination. Right, that would not form a bonding combination. But, right, what would happen if we overlap the pz orbital and the pz orbital? Well, if we do that, then, right, these two lobes are going to, these two lobes are going to interact with each other, right? The in-phase lobes there, right, and the in-phase lobes here are going to interact with each other. So here we're not going to have a head-on collision. Here we're going to have a side-on collision. So what would that look like? Well, we're going to have a side-on collision here, right, which means that this is going to be a pi bonding combination. All right? So our pz orbitals in this case are going to form a pi bonding combination. And I'm not going to erase it, so, right? Hopefully then you can also see, right, that our py orbitals are going to give a pi bonding combination also, right? Because these two lobes are going to overlap, and these two lobes are going to overlap here. And this is important, right? Just like on, a standard Cartesian coordinates, right? The x, y, and z axes are all 90 degrees from each other. The px, the py, and the pz are all 90 degrees from each other. So what I'm showing you is both the pz and the py orbitals here, these are all 90 degrees from each other. And these will make separate pi bonding combinations. Okay? So let's go up here. I'm going to do this a little bit differently, right? So I'm going to bring my py orbital here, right? I'm going to bring my py orbital here, right? Those two are going to come together. Okay. I'm going to erase this. You guys will see why in just a second, right? But my two py orbitals are coming together. So this is pi 2py. And then my z orbital, right, would make an equivalent pi bond, right? Pi 2py. Right, and I could bring in the dotted line from this pz orbital over here too. But we're making two pi bonds from the py and the pz respectively. Since they're two pi bonds, they start out at equal energy. They're going to end up as equal energy. Pi bonds have in this case, cough, cough, hint, hint, right? They're going to be at a higher energy than the sigma bond, okay? Of course, if we make a bonding combination, then we have the corresponding anti-bonding combination, okay? So pi star and pi star 2py and 2pz. Good? So if you guys want to pause here for just a second, what I'm going to do is erase these dotted lines just for clarity's sake. Just because I am no artist by any means, right? It's just kind of hard to keep all that stuff together. So this is, right, in the purple there, right, as we mix the red and the blue, right, we end up making the molecular orbitals from the corresponding atomic orbitals is what it is, right? And through the magic of digital, right, I'm just going to bring this up. I'm going to bring this down here, right, just to give a little bit of spacing. You know what, here. Fantastic. Now, we used to have to do this all on pen and paper, and right, we wouldn't be able to do this. Cool, you guys got it? Let's draw, right, let's draw what these looks like here, right, what these looks like. All right, well, clearly grammar isn't a forte at the moment, right? So remember, this is our combination of our 2p, whoops, I forgot to put that in there, apologies. This is our 2px orbitals overlapping, right? So we have x orbital here, right, and x orbital here that are going to overlap to make our new, right, our new molecular orbital, which will look pretty much something like this, right? And then we've got our little lobes kind of sticking out in the back there also. Does that make sense? Right? And then up here, right? This and this. This would essentially just look like this, right? Some kind of anti-bonding combination where we don't have something in the middle there. Okay? We would bring together the opposite phase, right? And then our 2py orbitals, these are going to be, sorry, this is going to be a challenge to draw, right? One of them is going to be pretty easy, right? Right, we have, whoops, we have this, right? And this. Right, these two come together to make our hamburger-looking orbitals, right? Where we have the density above, right, and below. And then here the z orbitals are coming out of the board at us here, right? So we have the lobe coming out at us, right? We have the lobe going back in, right? We have the lobe coming out at us, the lobe coming back in. Oh, I'm sorry, I'm drawing this in the wrong place for you guys. Oh, goodness, goodness, goodness. I hate this. All right, here's where my typo came in. Sorry. There it is. So let me move this around just a bit. Right, there's that bonding combination there. We'll leave that other stuff up there, right? And we'll move this here, right? Okay, so sorry about that. Apologies. If I had some time to edit all this, I would definitely edit that out. But anyway, sorry. So real quick then to clarify, this is my depiction of my 2py orbital bonding combination. My z orbitals are coming in and out of the board, right? So they're going to overlap, right? They're going to overlap to form the bonding combinations that look just like the py orbitals, right? That hamburger type shape, right? Except they're in front and in the back, right? So in the front we'd have, it should be in purple. In front we would have, you know, our hamburger bun, and then in the back, right, we would have the other orbital in the back there. Man, you certainly become an artist when you become a chemist. What can I say? All right, and for emphasis sake, anti-bonding orbitals. And don't worry, I've got a surprise for you guys in just a minute. Okay. The anti-bonding combination looks like, right, we'd have those coming together. This is going to look a little bit different maybe than what you expect. What happens when you bring these together, like the p orbitals kind of like bend away from each other. So they kind of end up looking like this, right? And I won't even try to draw it. If you imagine rotating that 90 degrees, it'll be the same as with the pz orbitals, right? So it's going to be just a little bit, you know, difficult for me to draw that. All right, we're still not done. Oh no. These take a while to draw, right? A while to draw and put together, but there's a lot of useful information from there. So if you want to pause here for just a second, make sure you can draw these, and does it make sense? Can you understand what I mean with the 90 degrees between the px, the py, and the pz? The hamburger buns, right, above and below and in front and back, all this kind of stuff, okay? But the next thing we need to do is figure out where in the world the electrons are living, right? So we're dealing with O2, right? Each oxygen has 6 electrons, so we have a total of 12 electrons we got to fill in. And those 12 electrons are going to get filled in, right, here to our new molecular orbitals, right? So start from the bottom, 1, 2, 3, 4, 5, 6, 7, 8. Okay, let me pause. Why did I fill them in like that, right? Remember, we always try to unpair before we have to come back together. So we have 8, 9, 10, 11, 12. All right. So that's what the molecular orbital diagram looks like for O2. Okay? So I'm going to take a quick pause here. You guys aren't really going to notice it on your end, of course. But I'm going to take a quick pause. I got to load something up in the background. I'm going to come back and I'm going to show you guys something pretty neat. Okay? So hang on just a minute. All right. Why isn't this working? Oh, there it is. Okay. So we're back. So what I did in the background, and if you want to know the software that I used and all this kind of stuff, swing by my office. I can show you what it is. So in the background, okay, let me do this for just a second. Okay, and that. Okay, so here's what we have. So what I did is I took oxygen and I put it through a series of softwares that would generate the molecular orbital diagram for me. So in the middle there, in the red, you see oxygen bound to another oxygen. And for those of you guys who are super observant, you're looking at this and going, hey, wait a minute, right? It's only got a single bond in there, all this kind of stuff. So the software doesn't care about single versus double versus triple bonds. It understands that based off of the calculations and the distance between it, it knows what the bond is and all this kind of stuff. So don't worry too much about that. Okay. Over on the right-hand side, let's see if I can bring in a right. Hopefully you guys can see that. You see orbitals over here. So these are the molecular orbitals. Now, for those of you guys who are super observant, you'll see we've got 28 orbitals here. Wait a minute, right? But we only did what over here, right? We had, 1, 2, 3, 4, 5, 6, 7, 8, right? We only had 8 orbitals. How in the world did we get 28? Well, remember when I said things get a little bit more complicated in reality? Here it is. Anyway, who cares, right? We don't need to worry about all 28 of those. What we really need to worry about, right, is right here at 8 and 9, where it says HOMO and LUMO, right, the HOMO and the LUMO. That's the highest and the lowest, right, HOMO, highest occupied molecular orbital, and lowest unoccupied molecular orbital. Most chemistry that we're going to be dealing with works at the HOMO and the LUMO there, all right? So we'll get that... We'll get that figured out a little bit later, you know, what exactly we mean with that. Anyway, here's what we did, right? So I ran it through this software and I said, please generate what the molecular orbital diagrams look like. So I'm going to turn on some axes here, right? So this red and the green, there's also another axis hidden underneath there, right? It's just showing us the Cartesian coordinates, right? So as I rotate this around, hopefully you guys can just see, right? That's just my X, Y, and Z arbitrary axes right there, right? That's just going to help us a little bit as we orient ourselves, here, okay? And then I'm going to turn on my surfaces. Now you see those little like kind of bluish looking things that kind of cropped in? If I get rid of this, right? So those blue things right there, those are the representations for the lowest, right? If you look over here, I'm at the lowest energy orbital that exists. And you notice how they look kind of spherical like that, right? So this is our 1s orbitals. You see there's no real interaction between those, right? Those are our core electrons. There's no interaction, but they are in phase. As soon as I move up, right, there's my out of phase interaction between my 1s orbitals for oxygen. You see the energy over here, negative 500? They're not doing anything, right? They're not doing anything, okay? But now we move here. All right. So you see now I'm going to bring back in my, you see how I have my atoms in there? Now you see we have an in phase, right? A blue kind of, you know, oblong pill-looking thing, right, that encompasses both of my atoms. So this is a bonding combination between my 2s orbitals. Let me tab back over here for just a second, right? We are looking at basically this right here, right? So we're essentially looking at that interaction right there. But it's not purple, you say, I know, right? Red and blue are just the phases that they use in most of these programs, but they don't overlap to make purple. It would be useful, but it doesn't really matter. I think you guys can understand here, right? So there's a bonding combination. We move up. There's our anti-bonding combination, right? My 2s orbitals interacting in my non-bonding combination. Anti-bonding combination. Aha! Now this looks kind of weird, right? So pause here for just a second, see what you guys can make out of this. All right? So in the middle, we have an overlap in blue there, right? In the middle, we have an overlap in blue between the two atoms. And then we've got these two red lobes on the outside there. So this is our overlap of our px orbitals, okay? So we are right here, basically, is what it is, okay? We have an interaction between the two atoms, and then on the outside we've got the remaining electron density. Now, as soon as we move up, right, watch what happens. Okay? You guys with me? Take a look at that green arrow that's drawn on my screen. I'm going to rotate this. What do you guys see, right? So now we have our hamburger buns. So this is one of our pi orbitals. Okay? Whether it's the pz or the py, it doesn't matter, right? I'm going to move up one more, right? And I'm going to rotate again. You see there's my other hamburger buns, right? So I'm going to rotate here, and I'm just going to tab in between the two, right? I'm not rotating, right? You see the green arrow there remains the same, right? So we see that these are just perpendicular to each other, 90 degrees. If you're looking over here on the right-hand side, you see the relative energy level, negative 11.81 and negative 11.82. There's probably just some error in the calculation, small error. These are essentially equivalent energy, okay? So these are two pi bonding combinations. Whoops, I'm sorry, right here. My two pi bonding combinations from my two p orbitals there. Now we're going to go here. Now what do you see? Okay, I'm going to tab in between, right? So here are my anti-bonding orbitals for my p orbitals. Okay, you guys see how that green arrow is always pointing towards you. I'm not rotating anything, right? I'm just showing you the two sets of orbitals that are orthogonal to each other. Okay, so this is my anti-bonding combination of the two p orbitals, which means I am sitting right here now. Okay, so you see how they're kind of angled away from each other. They're opposite in sign, but this is my HOMO and my LUMO. Okay, remember this is right now what you're looking at is the highest occupied orbital, and this is the lowest unoccupied orbital. And then as we continue to go up, right, there's my sigma anti-bonding, okay, which is this guy right here. And you say, hey, that looks a little bit different. You're right. I know. There's my sigma anti-bonding. And then, right, we see some weird anti-bonding from my p orbitals, right? You see how there's like multiple layers in there, right? That looks pretty weird. Let me get rid of this just to make it a little bit easier, right? That looks pretty strange. All right, we've got some weird orbitals kind of cropping up here. You guys can maybe start to see what's happening here, right? See that weird torus there in the middle. Ooh, that's cool. All right, so as we get up into these other ranges here, that looks super cool. But anyway, right, so these are higher energy orbitals that we're really, we don't really care about, right? So maybe you guys can see where these higher energy orbitals are coming in from, right? So this is a pretty good example right here. So these are our d orbitals, right? Our d orbitals. Hey, wait a minute. I hear you saying it already, right? I hear you saying it already. How in the world does oxygen have access to d orbitals? Well, the answer is it does and it doesn't, right? Technically speaking, all atoms have access to all orbitals. It's just practically speaking, right? Practically speaking, they're inaccessible energetically, right? If you take a look up here at LUMO plus 19, right? So let me render that, right? So this looks like it's probably coming from, well, I don't know, maybe my DZ squared or something like that orbital, right? It's at 97 electron volts. It's just not going to, right? You're just not going to access this orbital, right? It's anyway. But the point being, right? The point being that this is a good way to visualize the orbitals that we want here, right? So this is what we are representing with our, let's say, our pen and paper representations of these molecular orbitals, okay? So anyway, this video has been going on for a while here. Let's end it, right? We've got about almost 30 minutes in this video. I think that's a good place to pause, right? And we will pick this up next time, and we'll talk a little bit more about this, okay?